Good afternoon, everybody. Welcome to a damp, cold, rainy Wednesday afternoon of Chem 1105 with your host, me, Dr. White. Let me remind you, tomorrow morning about 8 a.m., give or take a little few minutes, I will send out an email to all of you with the password for the password protected PDF file of test number 2, which you can download from Blackboard. And you have until Friday, I think 4 p.m. or 3 p.m. I forgot what I put down, to take test number 2 and upload it as a single PDF file. There's an announcement covering all that. I've gone over it a couple of times, and you should have also gotten an email. Now, one of the things I want to do real quick, because I forgot I didn't do yesterday, was when on test 2, there will be some questions where you have to balance equations. And remember, you get the same number of atoms of each type on each side of the arrow. And my advice to you is do hydrogen, oxygen last. And if we look at number 7, forget about the coefficients. 1 aluminum, 2. So to get this to 2, I'll put a 2 in front. Here in the bracket, you multiply whatever is in there times what's outside to the subscript down right. And here it's 3. 3 times 1 sulfur, 3 sulfurs. To get 3 sulfurs, put a 3 there. Now 3 times 2 is 6 hydrogen. To get 6 hydrogen, put a 3 there. And finally, 3 times 4, 12 oxygen. 4 times 3, 12 oxygen. I'm done. And if you look at 6, same thing. Leave hydrogen, oxygen last. I think I've already done this one in class. Now, let's look at number 10. This is what I call an even-odd chemical equation. What do I mean by that? Forget about the coefficient initially. 2 oxygen, this side 3. There's no whole number I can multiply 3 by to get 2. There's no whole number I can multiply 2 by to get 3. Remember, coefficients are whole numbers, exact numbers. Therefore, what number do they both go into? And 2 times 3 is 6. So to get 6 oxygen here, put a 3 there. To get 6 oxygen this side, put a 2 there. But now I have 2 times 4 iron, and I do that. And that's how you do even odd. And I wanted to go through that. All right. Yesterday, when we finished up, I was talking about the Industrial Revolution. And that happened in the 1700s, especially in England, where new power supplies were found to drive equipment to make things in factories much faster than just by hand. And one of the sources of power to drive that machinery was the steam engine. Another one later on was the gasoline engine, and both deal with gases. And as I said yesterday, if you could predict and come up with an understanding what gases do under certain conditions, you could make some money, and they did. Well, the first one I want to talk about, and these are called gas laws. And a gas law is something that's always, always true. So if we look here, we have Boyle's law. And Boyle was an English chemist who studied gases because it was lucrative, money. Anyways, Boyle's law is the volume of a sample of a gas is inversely proportional to the pressure applied to the gas if the temperature is kept constant. What is that? Well, a better way of saying that or understanding Boyle's law is P1 times V1 equals P2 times V2. Now, give me a second, actually more than a second, because I forgot to open up something. Bad, Dr. White. And if you look on your screen, Boyle's law, P1 times V1 equals P2 times V2. Now, what is P1, V1, P2, V2? Good question. Thank you. All right. P1 is the initial pressure. V1 is the initial volume where you start. P2 is the final pressure, and V2 is the final volume. And Boyle's law is P1 times V1 equals P2 times V2. And pressure and volume can be any units of pressure and volume. They're not restricted to one thing. Now, this right here is in important information test number 3, which is coming up a week from tomorrow. A quick word to the wise. Things are going to speed up. Don't fall behind. Keep up with watching the videos and keep up with doing the practice problems. And don't forget to hand in your labs. So here's Boyle's law. Here it is. P1 times V1 equals P2 times V2. So let's have some fun with Boyle's law. Hold on, I gotta turn on my tablet. And it's on and installed. All right. All right, let's take a look at this. 8 points. Yep, 8 points. What happens to the volume of a balloon at 4.11 L is liters? L is liters. I don't want to write it there. we really haven't talked much about volume. We will next chapter, but L is liters. All right, what happens to the volume of a balloon at 4.11 liter and 7.83? And I made a mistake. I can correct easily. And 7.831 atmospheres if you reduce the pressure of the balloon to 3.117 atmospheres. Well, what do? You find out what are you being asked to find. Now, notice you have an initial pressure, initial volume, and then you're going to change the pressure to this. So what you're trying to find out is the volume after you do something. And that's the final volume, V2. We're trying to find V2. What are we given? The initial pressure, P1, 7.831 atmospheres. The initial volume, V1, that's where we started out, is 4.11 liter. And the new pressure that you change it to, that's P2, the final pressure, 3.117 atmospheres. Now, if we look at this right here, all you see are pressure and volume. And immediately that tells me I should use P1 times V1 equals P2 times V2, Boyle's law. Now, what are we trying to solve for? V2. We want it alone on one side. How do we do that? Well, anything divided by itself equals the number 1. So if I want to get rid of P2 because I want V2 alone on one side, I'll divide by P2. But anything you do to one side, you have to do to the other. And I will. Now this cancels out. So I'm left with 1 times V2, which is V2 equals P1 V1 over P2. Again, when you're solving for something, V2, for this equation, you want it alone on one side. So how do I get rid of the P2? Divide by it. Whatever you do to one side, you have to do the other. Now, you don't have to do this, but I do because I like to, and I will. And I'm going to rewrite this. V2 equals P1 times V1 over P2. And now, since I took the time right up here to figure out what is P1. Hi, Nubia.
Hi, Dr. White.
P1 is 7.831 atmospheres. V1 is 4.11 liter. And then P2, the final pressure, is 3.117 atmospheres. Now, before I pick up my calculator down here, I'm going to look that the units cancel out to give me the right units. And notice here, I have atmospheres, anything divided by itself equals the number 1, cancels out. What am I left with? Liters. Is that a volume? Yes. So I'm on the right track. And now I can pick up my calculator. And my calculator gives me this number. Actually, there are more, but I'm not going to write them all down. And remember, for all calculated answers, please use proper significant figures. And when you have multiplication division, you have the same number of significant figures in your answer as the number with the lowest significant figures that you multiply and divide by. This has 4 significant figures. 3, all non-zero numbers are significant. And this has 4 significant figures. And the question is, what's the smallest number? And hopefully we pick 3. So we have to round this off to 3. Keep the 1, keep the 0, keep the 3. Use the 2 to round off. Is that 4 or less or 5 or higher? And 4 or less. So I drop all this. And the correct answer would be 1.3 times 1/10 to the first liters. And that's how you use Boyle's law. Oh, this was fun. We got to do another one. Let's have some fun. Now, I have to warn you. Warning, warning. I'm going to do some artwork. My mother was a really good amateur artist. My father was a very good amateur carver. They both had artistic talent. Not one iota or bit of it rubbed off on me. So when I draw pictures, you can laugh your head off. It's allowed. All right, let's assume we have a cylinder with a plunger. We can call that a piston. And I have a gas in here. And what I'm going to do is push the plunger down. So let's look at this problem. And remember, these gas laws were developed for the steam engine and gasoline engine, which had pistons with gas in them. All right, let's look at this. 8 points. What happens to the pressure in a piston at 10.61 L liters of volume, 1.111 atmospheres, if you reduce the volume to 1.011 liters? Well, the first thing you should answer, what am I trying to find? Well, you're trying to find the pressure after you change the pressure, the volume in a piston. In other words, you're pushing this plunger down. So that's the initial pressure? No, that's the final pressure we're trying to find. What's the initial volume? Well, it's at 10.61 liters. What's the initial pressure? It's at 1.111 atmospheres. What's the final volume? When you change it to another volume, that's the final volume, V2. And that's equal to 1.011 liter. And once you have this, you don't have to look at this anymore. And I won't. So if you look at, we're trying to find pressure, P2. We're given two volumes and another pressure. Well, it only deals with pressure and volume, and that immediately should tell you that's Boyle's law. P1 V1 equals P2 times V2. If you look at important information, test number 3, P1 times V1 equals P2 times V2. P1 initial pressure, V1 initial volume, P2 final pressure, V2 final volume. So what do? I use that. Now, what are we trying to solve for? And the answer is P2. We want it alone on one side. That's how you solve it. Uh-oh, I got to get rid of V2. Remember, anything divided by itself equals number 1 is gone. So if I divide this by V2, it's gone. I'll have P2 alone on one side. However, whatever you do to one side, I have to do to the other. And I did. Now, V2 divided by V2 equals 1. 1 times P2 is P2. And this is P1 times V1 over V2. Now, you don't have to do this, but I do because I like it. And I'm going to rewrite it. And now, since we took the time, what's P1? Well, we took the time right over here to figure it out. That's 1.111 atmospheres. What's V1? And that's 10.61 liters. And what's V2? Well, we took the time to figure that out. That's 1.011 liters. Now, before I pick up my calculator, I'm going to just look at the units. Notice in the bottom here, I have liters. And over here, I have liters. And anything divided by itself cancels out, equal number 1. So the unit liter cancel out. What am I left with? Atmospheres, that pressure? Yeah, I'm on the right track. So now I can pick up my calculator, clear it. 1.111 times 10.61 divided by 1.011. And the number my calculator gives me is this. And remember, when you're doing any multiplication division, you should have the same number significant figures is your answer as the number you're multiplying, dividing, that has the smallest significant figures. This is 4. Ooh, this is 4. This is 4 significant figures. So what's the lowest number? Well, they're all 4. So we have to round this off to 4 significant figures. And here, keep the 1, keep the 1, keep the 6, keep the 5. Use the 9 to round off. Is that 4 or less or 5 or higher? And 5 or higher. So I'm going to drop this and increase the number in front, the 5, by 1. And the correct answer is 1.166 times 10 to the first atmospheres. Or if we wrote it in decimal, 11.66 atmospheres. So let's take a look at this. We started with this pressure. We end up 10 times greater. That's because we pushed the plunger down and brought the gas together by lowering the volume, and that increases the pressure. Now, one of the things I'm going to be asking you to do more and more this semester, as I cover things more, how should I say, common in your daily life, you should ask the question, why am I learning this stuff? Well, the obvious answer is someone said you have to take Chem 1105 to get a degree or to get into school. So that's why you're taking it. But why should we learn this? Well, let's take a look at this. By pushing the plunger down, by moving the plunger down, reducing the volume, you've made the pressure go way up. What does that look like? How many of you have ever used a hand pump to inflate a basketball, bicycle tire, football, volleyball? Have you ever done that? You push like this. And they have a valve at the bottom that when the pressure is high enough, it opens up and pushes that gas into whatever you're trying to inflate. And you're inflating something, putting gas under pressure. Now, how many of you have ever gone to a gas station, or you have one at home, like I do, and have what's called a compressor? And you see the device, you press the button and it makes a lot of noise. You take the hose with the attachment, put it on your car tire stem, and it inflates the tire. How does that work? Well, it's a piston like this, except it's on an electric motor. And it fills what's called another tank called the ballast to have high pressure air. So next time you happen to pump up a bicycle tire, or you happen to see a compressor in a gas station, remember, this is using Boyle's law. P1 times V1 equals P2 times V2. Now, in the past, you'd have to memorize this if you were in my class for test number 3. Good news. It will be an important information. Test number 3. So you don't have to memorize it, but you do have to know how to use it. All right, let's move on. We've done our Boyle's law practice, and I'll do 1 or 2 more when we go through the practice problems for this chapter, probably Monday. Now, listen carefully. Click. The switch is off for Charles' law. And Charles' law is similar to Boyle's law in the sense it deals with gases. Here, the volume of a sample of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. And Boyle's law, Charles' law, excuse me, is V1 over T1 equals V2 over T2. V1 initial volume, T1 initial temperature, V1 final volume, T2 final temperature. Now, years ago, whenever I put Charles' law problem on the test, almost every student got it wrong, because solving for V2 or T2 is much more complex here. So guess what? Oh, by the way, don't forget Kelvin is degree C plus 273. Charles' law will not be on any test or final exam. Remember, the switch was totally off. All right, I like to talk about something that's important in our daily life. And I'll be doing some definitions which you do not have to know, but I'll tell you when you should know things. Now, let's talk about vapor pressure and boiling point. How many of you have ever seen water boil? I hope all of you. And I will talk about things on vapor pressure and boiling points that are not even in your text. See, Dr. White knows chemistry. I can do that. All right, let's talk about liquids. You can have a liquid evaporate. If you put some water on a desktop or a table and come back in a day or two, it's gone. It evaporated. And that's the process in which molecules escape from the liquid phase to the gas phase. The liquid molecules become gas molecules. We call that evaporation. Now, the rate of evaporation is dependent on the temperature. Evaporation happens at a quicker rate for hotter liquids than cooler ones. And when evaporation happens, the remaining liquid gets cooler. In a little while, I'll talk about sweating and cooling towers. By the way, men sweat, women perspire. All right, now, when we talk about certain compounds in a gas stage, especially water, we call that a vapor. Again, click, switches off, and the gaseous molecules of a substance at a temperature and pressure that at which it would ordinarily be thought of as a liquid or solid. So if you boil water, the gas above it that's coming out of the water, liquid becoming gas, we call that water vapor. How many of you have ever seen in a cold winter, if you're boiling water in the kitchen, you can see your windows steam up? We call that. Or if it's a real cold winter day, you're taking a nice hot shower. Dr. White likes nice hot showers. Your mirrors sometimes will steam up, and that's the vapor condensing on there. All right. Now, switch is still off. There's something called an equilibrium. And I teach this more in depth in Chem 1211, but not really much in this class. So again, switch is off, click. That's a condition in which two opposite processes take place at the same rate. Now, vapor is a gas. In this case, I'll talk about water vapor, and any gas can have a pressure. And that's the pressure exerted by the vapor above the liquid. That's the vapor pressure when the liquid and vapor are in equilibrium. Switch is still off. What does this mean? Here's my beaker of water. And if you're at room temperature, like now, some of the molecules of the liquid water become gas. And at the same time, some of the gas here become liquid. And when the rate is the same, how much becomes a gas, how much becomes a liquid, the pressure is called the vapor pressure of that gas. Now, again, switches off. There's something called the volatile substance. That's the substance that readily evaporates at room temperature because it has what's called a high vapor pressure. Water doesn't, gasoline does. Don't try that at home. All right, now let's talk about boiling. I think you've all boiled water to make something like noodles, rice, or other things you cook in boiling water. And that's a special form of evaporation where the conversion from liquid state to vapor state occurs within the body of a liquid through bubble formation. I'm going to do a beaker, but you probably have done it in a pot or pan. Oh, by the way, don't hurt yourself laughing too much. This is a beaker of water on a hot plate. You heat it, and what are you going to see inside here? Little bubbles. Let's magnify them. There's a little bubble. And what's inside this bubble? Water vapor. And when it comes to the surface here, it collapses and releases that water vapor. If you don't believe me, watch a pot of boiling water next time, and you'll see the bubbles come up and collapse. And that's called boiling. Now, there's an important concept switches on, and that's the boiling point or temperature of a liquid. That's the temperature at which vapor pressure of a liquid becomes equal to the atmospheric external pressure on the liquid. So if I'm here in Chicago land and the atmospheric pressure is a certain amount, and you're heating water, when the vapor pressure equals atmospheric pressure, if I were to stick in a thermometer, when the vapor pressure equals the atmospheric pressure, that's the boiling point of a liquid. Now, I'm not going to ask you normal boiling point is the temperature at which a liquid boils at 760 millimeters of mercury, which is sea level. All right, but I will ask you to know the following. Click switches on. And if you go to Denver, what happens to the boiling point of water? Well, Denver is called the Mile High City. I've been there a number of times on business. And when you go that high, when you go higher altitude on our planet, when you go to higher altitude, that means the atmospheric pressure is lower. Since the atmospheric pressure is lower, you need less energy to get the equilibrium, the vapor pressure to water equal the atmospheric pressure. And therefore, you should know in Denver, is lower. Let's see if I can find out exactly how lower. All right. At sea level, the boiling point of water is about 100 degrees C. At Denver, which is the Mile High City, about 5,000 feet above sea level, it's 95 degrees. If you go to the Himalayas, which is probably about 15,000, the boiling point is 84.5 degrees C, a lot lower. The higher you go in the altitude, the lower the boiling point. And you should know this. Hold on. All right. The higher the altitude, the lower the boiling point of water is, because at a higher altitude, the atmospheric pressure is lower. Therefore, it takes less energy, heat, to get the water vapor from the bubbles when you're boiling water, that pressure, vapor pressure, to equal atmospheric pressure, which is by definition, when the vapor pressure equals the atmospheric pressure, that temperature is the boiling point of that liquid. Now, how many of you have ever seen a pressure cooker? And pressure cookers work by cooking things you cook in them faster. How? Inside the pressure cooker, the pressure is very high. So any water in there, when it boils to heat, is going to be a lot higher than 100 degrees C. And a higher temperature in the pressure cooker means it gets cooked quicker. Oh, you have one, Julia. Now, one of the things I didn't mention earlier is, have you ever been in summer when it's high humidity and you've been working out and you're sweating like you're dripping? When I played tennis, it's been a while, I'd always bring a couple of towels out to the court when we play in the summer, because headbands, forget about, I'd be just dripping in high humidity. Why? Your body cools itself by putting liquid here, we call that for men sweat, women your perspiration, and it evaporates, and that cools down your skin, your body. Well, if there's a lot of moisture in the air, high humidity, it doesn't evaporate that easily, which is why your body keeps on putting more water on there. Come on, evaporate so I can cool this guy down. All right, now turn the switch off next couple slides. There's something called Avogadro's law. Ooh, I've heard that name before, Avogadro's number. That's because he investigated the relationship between volume of a gas and moles. And the volume of a gas is directly related to the number of moles of a gas when temperature and pressure are not changed. This can be derived by the ideal gas law, which I will teach you today. And at STP, and again, switch is totally off, standard temperature and pressure, these numbers, 1 mole of a gas equals 22.4 liters, switch is off. I've never used that in anything I've ever done. But now, this is probably the most important mathematical equation, or my favorite one, in chemistry, the ideal gas law. And that's PV equal nRT. P is pressure in atmospheres, V is volume in liters, N is the number of moles, T is temperature in Kelvin, and R is the universal gas law constant, which is a calculated number. And for this class, we'll use 0.0821 atmospheres liters per mole K. If you notice, it says learn this. In the past, you would have to memorize this. I will give this to you in important information, test number 3. But I just looked at the clock. It's time for a break. Let's take about a 5-6 minute break, and we'll come back and finish talking about the ideal gas law. I'm back. Profound, if you couldn't tell. All right, let's look at the ideal gas law. And the ideal gas law is PV equal nRT. P is pressure in atmospheres, V is volume in liters, N is the number of moles. But you're going to give in weight, so you're going to have to know how to go from weight of a compound to moles, which I hope you learn for tomorrow for test number 2. You'll need that. And T is temperature in Kelvin, but you'll always be given degrees C, Celsius, and remember, Kelvin is degrees C plus 273. And R is the universal gas law constant, always the same, 0.0821 atmospheres liter mole K. Now, in the past, you'd have to memorize this. Good news. Here it is, important information, test number 3, PV equal nRT, and I tell you what pressure, volume, and T and R are. R squared, whatever, sorry. But let's take a little look at this. Sorry about that. And what I'm going to go over now, you should know. I'm assuming you've all seen a car tire. And a car tire is just a balloon. It's a container that has gas in it. I know they've tried to make some car tires that were solid, but I haven't seen on the street. I don't think it's panned out. Well, it turns out PV equal nRT, the ideal gas law, teaches you when you should check the pressure of your car tires. Now, time for a Dr. White story. Many years ago, wow, many years, I think it was 1995. Wow, that's a long time ago. I lived in the other part of Schaumburg in a apartment complex. I hadn't bought my house yet. And you parked outside in the parking lot. Well, it got one Friday night, it got brutal cold. I mean, the temperature that night went down to below 20 below or even a little colder. I'm not talking about the wind chill, I'm talking about the cold. It was cold. And I won't teach this in this class, but the colder your battery gets, the less energy it can put out. And it's good on cold weather to start your car driving around to charge up your battery. So Saturday morning, about 8 in the morning, I figure I better go out and drive my car around so the battery doesn't go dead. So I go out to my car in the parking lot, and I look, all 4 of my tires are real low, like they're almost flat. Oh no, I have 4 flat tires. No, took about 1.5 seconds and my brain clicked in. Ideal gas law. I know the problem is. I went over to gas station to fill my tires with car, and then I drove my car around for a while to make sure the battery was charged up. Luckily it was. But by the time I finished filling my car tires, I looked up and there were 10 other cars in line. And this is like 8:15, 8:20 in the morning and super cold out. What happened? Well, in your car tire, there's a gas, and that gas follows the ideal gas law. And in winter, what happens to the temperature? it gets cold, it goes down. Well, PV equal nRT, ideal gas law. In your car tire, unless you get a flat, and I hope you never do. I've had a few in my life. They're never fun. Your volume of your car tire is constant. The moles of the gas is constant. And R, the universal gas law constant, is constant. So if the temperature goes down in the winter, the only thing that can change is the pressure, and the pressure will go down. And that's what I saw. Those tires got super cold and the pressure went down because PV equal nRT. Temperature goes down and PV equal nRT in your car tire, the pressure will go down. Now, about that same time, and I think the cold temperature was actually earlier in the early 1990s, but at about 1995, here in Chicagoland, I know that to be true, in the summer, it was a brutal summer. For a good 2 weeks, the daytime temperature was never below 100 degrees Fahrenheit. Oh, it was bad. And because of that, I think in Chicagoland, over 500 people died because of the heat. Now we have cooling centers where if you don't have cooling, you can get out of the heat to go places. I know in the summer when it's really bad, College of DuPage opens up their main large buildings like our building and where the chem department is as a cooling center. Well, back then they didn't do this. And in the summer, what happens to the temperature? It goes way up. Well, in your car tires, the gas follows the ideal gas law, PV equal nRT. In your tire, V, N, and R stay constant. So if the temperature goes way up, the pressure goes way up. What does that mean? In the summer, if it gets real hot, like in August here, you better keep an eye on your car tire pressure. Now, that year, I lived in Schaumburg and I worked at a place called PPG Mazer, which was by Great American Gurnee. So I had a long travel on the toll roads, and you saw that summer in the afternoon, a lot of cars and trucks pull over with blowouts. What happened is they didn't check their car tire pressure and it expanded and blew up. So you should know in the winter, temperature goes down, and the ideal gas law teaches you check your car tire pressure because it's going to go down when it gets real cold. In the summer, temperature gets hot, goes way up. And you should keep an eye on your car tires because PV equal nRT, the pressure will go up because V, N, and R stay constant in your car tires. So remember that, know this about the ideal gas law. But let's have some fun with the ideal gas law. Now, I think you all know what a burp is. I'm not going to burp for you. No, that would be insensitive and crude and not nice. But when you burp, most of the gas you burp out is carbon dioxide. So let's have some fun with the ideal gas law. Yep, 15 points. And like I said, let's have fun with this. If you burp 1.27 grams of carbon dioxide at 758 torr and 37.0 degrees C, that's body temperature, what is the volume of your burp? Well, how do you proceed? Well, what are we trying to find? A volume. If you notice two things here, nothing changes. The amount, the pressure, temperature, everything stays the same. And hint, 15 points. I'll explain that in a little while. So we're trying to find volume of the burp. What are we given? 1.727 grams of carbon dioxide. What's your burp? You're given a pressure, 758 torr. You're given a temperature, 37.0 degrees C. And when you see this, nothing is changing, plus it's 15 points, you know you need to use the ideal gas law, PV equal nRT. Now, P is pressure, and let's go to important information, test number 3. P is pressure, but it has to be in atmospheres. You don't have that in atmospheres, so you're going to have to convert it. V is volume in liters, and I'll always give it to you in liters if I give it to you. N is the number of moles, but you have a weight, so you're going to have to convert weight of a compound to moles of a compound. You have temperature in degrees C, but you need it in Kelvin. If you do not have these variables in the right units, PV equal nRT will not work. You'll get the wrong answer. So let's get moving because we got a lot of work to do, which is why it's 15 points. Now, the first thing is we want to solve for volume. What does that mean? You get that alone on one side. How do I do that? Well, anything divided by itself equals the number 1, cancels out. I want to get V alone, so I want to get rid of P. Well, if I divide by P, that will cancel out. Whatever you do to one side, you have to do to the other. P divided by P is 1 times V is N R T over P. Well, now we have to figure out what's N. We're given R, and in R, here's R, so we don't have to do anything with that, but let's get to work. N is moles, in this case, CO2. So we have 1.27 grams of CO2. We want to get to moles of CO2. And how do we do this? Well, if you have a ratio that you can multiply and divide to convert the grams to moles, use your good buddy, good friend, unit analysis. Moles of CO2 go on top. Grams of CO2, carbon dioxide, go underneath. And where do I get this relationship between moles of a compound and grams of a compound? Well, in case you forgot, oops, wrong thing. Sorry about that. Important information, test 3, 1 mole of a compound equals its molecular weight of that compound in grams, and the molecular weight is the sum of all atomic weights. Well, I better open up my periodic table because I need to determine the molecular weight of carbon dioxide. And just like in test number 2, test number 3 will say under your name, please use proper significant figures for all calculated answers, and please use 3 significant figures for all atomic weights. Carbon is 12.0, the 3 significant figures. Oxygen is 16.0, the 3 significant figures. So we need the molecular weight of CO2, 1 carbon, 2 oxygen. 1 times 12.0, the atomic weight of carbon, 2 times 16.0, the atomic weight of oxygen. And that's 12.0, 32.0, and we get 44.0. Since both of these have 1 significant figure to the right of the decimal, our answer is correct. And here we have 44.0. And now notice grams of CO2 divided by grams of CO2 cancel out. We're left with moles of CO2. So now 1.27 divided by 44.0. And my calculator gives me, and I'm going to round it off for you because we got a lot of work to do. That would be 2.29. Remember, this is 3 significant figures, 3 significant figures, exact number. And when you multiply and divide, you get the same number of significant figures in your answer as the number with the fewest significant figures that you're multiplying and dividing. And I rounded it off to 3 significant figures. So now we have N. R is right here, so we have R. Next, we'll need temperature. And temperature, let's go back to important information, test number 3. And temperature has to be in Kelvin. In case you forgot, I have here an important information, test 3. Kelvin equals degrees C plus 273. So temperature in Kelvin, that's not ink, it's in K, equals degrees C plus 273. And we have in degrees C 37.0 degrees C plus 273. And that equals 300.0 Kelvin. If I did my math right. Nope, I didn't do my math right. Hold on, I'm going to check it on my calculator. Yep, this should be, sorry about that. Now it pays to show your work, because if you made the kind of mistake I did and everything else was correct, I'd take off 1 point for a math error. And I see a question. Yep, thank you, Yulia. See, even Dr. White will make a mistake. So we now have temperature in the right units, and we now need pressure. And pressure we have in torque, but if you look at important information, it's the wrong place. Test number 3, pressure has to be in atmospheres. So what do I do? Well, and we did this earlier. To get pressure in atmospheres, we have 758 torr. We want to get the atmospheres. And now we use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of this ratio. Whatever we're trying to get rid of goes underneath. So we have atmospheres and torr. And where do we get these numbers that go in that ratio? Well, in the past, you'd have to memorize it. Good news. If we go to important information, test number 3, 760 torr equal 1 atmosphere, also equals 760 millimeters of mercury. 760 torr equal 1 atmosphere. So for every 1 atmosphere, there's 760 torr. Remember, both of these are exact numbers. And I will now clear my calculator. 758 divided by 760. And I will round this off to 3 significant figures, because this is 3 significant figures. These numbers are exact numbers, and they don't play a role in there. And you get 9.97 times 10 to the minus 1 atmosphere. Am I done? No. I'm going to rewrite this over here. Volume, which I'm trying to find, equals nRT over P. And now my moles, which we calculated here, is 2.89 times 10 to the minus 2 moles of CO2. Next, we have the universal gas law constant, which is right here. And then we have our temperature in Kelvin, which is right here. And this all will be divided by, sorry about the non-straight line, anyways, by the pressure, which we calculated here. Now, if you look right here and get your magnifying glasses, forget about the bottom here for now, unit-wise. Just look at the top, moles divided by moles. And Kelvin divided by Kelvin. So on the top here, can't see it, I'll magnify it. What's left is this, atmospheres times liter. But underneath now we have atmospheres, we have atmospheres that would cancel out, and we're left with liters, which is a measure of volume. So let's do some 2.89 blue double E minus 2 times 0.0821 times 310.0. I'll divide that by 9.97 blue double E minus 1, and the number I get is equal to 7.37747 times 10 to the minus 1 liters. Now, this is one of those multiple step calculations. We did a lot right over here. And you can round off at each step, and I'm a round off at each step person, or you can wait till the very end. And I will calculate it both times here. I'm only doing it one way. And this is, remember, when you multiply and divide, you get the same number of significant figures, and the answer is number with the fewest significant figures. This is 3 significant figures. Universal gas law constant I use is 3 significant figures. You can find it's at 8 or 9 significant figures, but we don't need that. And this is 4 significant figures, and this is 3 significant figures. So we'll round that off, what? To 3 significant figures. Keep the 7, keep the 3, keep the 7. Use this 7 to round off. It's 5 or higher. I'll drop this, increase this by 1. And the correct answer would be 7.38 times 10 to the minus 1 liter, which would be about 0.7 or 730 milliliters, which would be, are you ready for this? About the volume of this gas bottle. That would be one heck of a burp. Wow, would that be a burp? That'd be a monster burp. But see, you can have fun with PV equal nRT. And let me remind you, this is a lot of work. Yes. And that's why this is 15 points, because you've got to do a lot of work. And hint, you should know how to do this for test 3. Well, since that's the case, let's do another one and have some fun with PV equal nRT. Where else can we find gas? A car tire. Let's have fun with a car tire. Let me change one thing. All right, let's do this. Again, 15 points. Why? Because it's a lot of work. All right, if a car tire contains 11.5 grams of nitrogen gas, I don't know, for about the last 10, 12 years, dealerships, if you want to pay extra money, will put in nitrogen gas to inflate your tires as opposed to air. Now, I personally don't do that, but some people feel it's better for your car tire. I just don't. But let's do the problem. So if a car tire contains 11.5 grams of nitrogen gas, and I could have written here gas, at 25 degrees C, 752 torque, then what is the volume of the gas in the car tire? All right, why don't you try and figure out what are you trying to find and what are you given? Your turn. All right, my turn. What are we trying to find? The volume, V. Now we're given a weight, 11.5 grams of nitrogen. We're given a temperature, 25 degrees C. And torque is the unit of pressure. And one other thing you'll be given from important information, test number 3, is the universal gas law constant, 0.821 atmospheres liter mole Kelvin. Well, if you look right here, is anything changing? No. We're dealing with a gas. And hint, 15 points. Oh, I gave it away. And because you're dealing with a weight, a volume, temperature, pressure, and nothing is changing, PV equal nRT, the ideal gas law. What are we being asked to solve for? V. I'm going to let you try, and in 2 steps, what would V equal to? Your turn. Solve for V. All right, looks like everybody's done. So how do we get V alone on one side? I should really go like that, so it looks more like a V, not a U, but it's a V. Well, we got to get rid of P. And somebody already got it right. Yay for that someone. All right, so to get rid of the P, to get V alone, anything divided by itself is number 1. So if I divide P by P, it's gone. But whatever you do to one side, you have to do to the other. So now we know V equals nRT over P. And now we have to find nRT and P. Important information, test number 3. Remember, pressure has to be in atmospheres. You're solving for V in liters. N is the number of moles. T is the temperature in Kelvin. So N is moles of N2. And what do? We have 11.5 grams of N2, and we're trying to get to moles of N2. What units go on top and bottom of that ratio? I'm going to let you have a lot more fun and hand in doing this to help Dr. White out. Again, not the numbers, just what goes on top and bottom of that ratio. Remember, use your good friend, your good buddy, unit analysis. All right. Using your good buddy, your good friend, unit analysis, whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And where do I get a relationship between moles of a compound and grams of a compound? Well, in case you forgot, and I hope you learn for tomorrow, but in test number 3, 1 mole of a compound equals the molecular weight of that compound, and the molecular weight is the sum of all atomic weights. Well, I need the atomic weight for nitrogen. If I look at my periodic table, remember on test 3, like test 2, it will say, please use all atomic weights to 3 significant figures. And 14.007 rounded off to 3 significant figures is 14.0. So for every 1 mole, I need the molecular weight of nitrogen. And the molecular weight of nitrogen gas is 2 nitrogens. Each one, whoops, forgot the 2, is 14.0. Do the math. So 1 mole is 28.0 grams. Grams of nitrogen divided by grams of nitrogen cancel out. I'm left with moles of nitrogen. Now I can pick up my calculator, turn it on, clear it. And I get a long number. I'm going to round it off because we got a lot more work to do. 3 significant figures, 3 exact number. All right, so I got N. R is right here. T is temperature and has to be in Kelvin. That's not ink, in Kelvin. And in case you forgot, am I being nice or what? Don't answer that. Kelvin equals degrees C plus 273. So Kelvin, my temperature, equals degrees C plus 273. My temperature is 25 degrees C plus 273 equal 298 Kelvin. And the last thing I have to figure out is pressure right here. Now, once again, is critical when using PV equal nRT, you have the right pressure. And for this, pressure has to be in atmospheres. Oh no, I've never seen a gauge in atmospheres, but you'll be given either torr or millimeters of mercury. So now, pressure in atmospheres, we have 752 torr. We want to go to atmospheres. What units go on top and bottom of that ratio? Your turn. Again, not numbers, just what units. Use your good buddy, your good friend. I see someone use their good buddy, their good friend, unit analysis. And I'm going to use it. When you use your good buddy, your good friend, unit analysis, whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And I'll write that. Not in red, though. And where do I find a relationship between ATM, atmosphere, and torr? Good news. Look at important information, test number 3. 1 atmosphere equals 760 torr. 760 torr equal 1 atmosphere. And now I can go back there. And I know for every 1 atmosphere, it's 760 torr. Now, don't forget, both of these are exact numbers. And this is 3 significant figures. So our answer should be 3 significant figures. And now I'll do the math. 752 divided by 760. And my calculator, and I'm going to round it off to 3 significant figures, gives me the following number. That looks nicer. So now I have everything to continue on. And I'm going to write this down here. V equal nRT over P. N we found was 4.11 times 10 to the minus 1 mole. Again, we're trying to find the volume of nitrogen in a car tire. R is the universal gas law constant, which you will be given. And temperature, we figured out right here. And remember, these have to be in the right units. And finally, the pressure in atmospheres we have here. Now, before I pick up my calculator, forget about the bottom number here. Just look at the top 3 numbers. Moles divided by moles cancel out. This is a K. Kelvin divided by Kelvin cancel out. Now I'm left on top here, and I'll write it here so you can see it better. Atmospheres liter. And here I have atmospheres on top. I have atmosphere. That would cancel out. And I'm left with liters. Yay, that's a volume. So now I can happily pick up my calculator and take 4.11 blue double E minus 1 times 0.0821 times 298 that equals something. Divide that by 9.89 blue double E minus 1. And the number I get now, this is 3 significant figures. 3 significant figures. I'm in my 3 significant figure rut. They all are. So I'm going to round this number off to 3 significant figures. And that's 1.02 times 10 to the first liter, which is also 10.2 liters, which is about the volume of a car tire. So remember, PV equal nRT. When you have a gas problem, hit 15 points. And nothing is changing. The volume, the weight, the temperature, the pressure, and the universal gas law constant better not change. You know you have to use PV equal nRT. However, the gauges we have that we measure, like temperature, pressure, or weight, are not in what we need, where N is moles, T is in Kelvin, P is in pressure atmospheres. And you have to do these conversions. And that's why this is 15 points. It's a lot of work. A lot, but it's 15 points. So I highly recommend you learn how to do this. Oh no, I looked at time. We're out of time. Boy, time flies when you're having fun with the ideal gas law and other laws. Well, with that, don't forget tonight I have my office hours, 7 to 8 p.m. Also, tomorrow morning, I will send out around 8 a.m. the password for test number 2 PDF file, which by Friday afternoon, 4 p.m., you should upload the answers. Take as much time as you need. Normally, that takes about 45 minutes for students who have studied and done the practice problems. And with that, I'll remind you, don't forget, hand in your labs. And tomorrow we'll have a lab. We will still have a class, and we'll continue on with gases, and we'll get into something else really cool, solutions. With that, I'll say, Gang gesund, goodbye. Stole that from Granny to Beverly Hillbillies.